feel like I am a dream killer. When people show up on my YouTube channel and they've had their head filled with science fiction, warp drives, stargates, all these ideas to travel faster than the speed of light, and I have to sadly inform them that it's probably not going to be possible. We have to violate various laws of physics to accomplish these ideas. But I want to offer everybody a ray of hope today, and that there are people working on ideas that might not be able to take us faster than the speed of light, but at least get us moving a significant fraction of the speed of light to make interstellar journeys happen within our lifetimes. And, there's nothing that breaks the laws of physics to be able to get to Proxima Centauri or other star systems in a human lifetime. So one of the people who is working on some of these ideas is Andrew Higgins, and he is a mechanical engineer, a professor at McGill University, and has spent a lot of time thinking about different ideas. He recently wrote a really fascinating paper about exploiting the differences in velocities of the solar wind as a way that you could maybe accelerate a spacecraft to 2% the speed of light just within the solar system, and then other ways that you could go maybe 20, even 30% the speed of light as you're traveling in the gulf between star systems. So I may have killed your dreams, but now I offer you these ideas as a way to make it up to you. And hopefully you will be as inspired by listening to Andrew talk about what's possible as I was. And hopefully we can see humanity reach out to other star systems within the next few decades and not the hundreds of years that I had originally been expecting. All right, enjoy the interview. Do you get to this point where you realize just how big the universe is and how far away all this stuff is? Does it make you sad? Does it make you happy?
Okay, yeah, I don't worry about the universe too much, but I do spend an awful lot of time thinking about the nearest stars, and we know there's exoplanets there now, and how can we get there? So I'm an engineer, so I think about how could we get there?
Well, I like this idea that stars pass relatively close to the Earth every few million years. And so if you're patient, many of the engineering challenges just go away. Right?
Well, yeah, that'd be a real test of your patience.
Absolutely. Yeah. You'd be looking at, tens of millions of years, but you don't have to wait. You don't have to travel 4 light years. You only have to travel 1/100th of a light year as a star is disrupting the planets inside the solar system.
Now that has interesting implications for panspermia, and could life have jumped from star to star and so on. So that's an interesting question, but those of us that work in the interstellar travel propulsion community, we're a little more impatient than that. We want to get there. It's nice to see something, in my lifetime. I'm taking my omega-3 every day and working out, doing everything I can so that I'll still be around when we launch the first probe.
Well, give me a sense of scale of like how difficult it is to travel to other stars compared to the kinds of exploration within the solar system that people are familiar with.
Right. Yeah. I mean, a really good example is to try to acquaint yourself with one of these scale models of the solar system. So there's one at the University of Colorado Boulder I like very much. In the middle of the campus, there's this sort of grapefruit-sized golden sphere that represents the sun. And then you walk a few feet away from that. There's a little pedestal with a little grain of sand on it. That's Mercury. A few more feet, Venus. A few more feet, you get to Earth, a little tiny peppercorn. And you're like, wow, that's how big the sun is. But then you look up in the sky and realize, oh, yeah, that's right. That's to scale. It has the right size. Then you got to walk, a block or so to get to Jupiter. And then you're more or less halfway across campus by the time you get to Pluto. And then at that last plaque, it says that on the scale of this this model of the solar system, the nearest star, Proxima Centauri, would be located where the Panama Canal is in relation to Boulder, Colorado. Okay,
Right.
thousands of kilometers. So I did something similar here in Montreal. I did a little scale model of the solar system at about the same scale. So you walk about 6 blocks from McGill to get to Concordia University. That's where Pluto would be. And then on that scale, Proxima Centauri is almost where you are out in Victoria. In Victoria, it's end up being somewhere in the Fraser Valley. Actually, is where you end up on that scale, right? So it's tens of thousands of times further than we've ever sent any spacecraft. And so what that means is we have to go tens of thousands of times faster to get there on human lifetime scales.
On human lifetimes, right. So when we look at the kinds of propellant systems that are available to humanity today, I mean, we've got the chemical rockets, we've got ion engines, maybe nuclear rockets. How do they all fall short of the goal of being able to reach another star?
Yeah, they all fall short. So chemical, very easy to discard that. If you just play with the rocket equation, the Tsiolkovsky equation, you quickly find out you'd need more propellant than the mass of the universe to do a mission to a nearby star in a lifetime. And ion propulsion, yes, you can get very high specific impulses, but then where does the power come from? So aerospace engineers, we tend to get really excited about the rocket and the exhaust velocity, but you have to remember, wait, where's the power going to come from? And just the power restrictions alone limit you. So if you look at really dense power sources, that points you to nuclear fission, nuclear fusion, and even there, it's a stretch. So a nuclear rocket, either fission or fusion, there's advanced versions of it that could probably get you to 1% the speed of light. But that's still not enough to get you. It still will be then hundreds of years to get to the nearest stars. So really, the two ideas that are out there that I think probably Plan A and Plan B. One is the laser-driven light sail. So this is the concept that the Breakthrough Starshot is based around. And then the other one, the other energy source that is dense enough, or energy storage medium that is dense enough to build a rocket around, is antimatter. So there, the biggest problem is how do we make the quantities of antimatter that would be needed? But there's work going on in that area. So before, people used to think it was hundreds of kilograms of antimatter, but now there's been some new developments that think we might be able to do it with much, much less.
Like, how much less? Like, if you wanted to make a journey to Alpha Centauri and actually go into orbit, how much antimatter do you think is realistic?
Okay, so first of all, let's agree we're going to talk about a probe. So we're going to talk about not sending humans. We're going to talk about sending maybe not even a Voyager-class spacecraft. We're going to rely upon miniaturization. So all this thinking now, the Breakthrough Starshot and other concepts I'll talk about, we're all going to bank on miniaturization of spacecraft and using the technology that's gone into our smartphones to make a spacecraft that's maybe tens of kilograms or maybe even just grams. And then to use antimatter, the most promising concept, this is work that's been done by Joel Jackson, who has a company called HBAR Technologies. And this was work that was funded under the NASA NIAC program that I know you're a big fan of. Most of your listeners know about NIAC. So the idea was to not use the antimatter directly, but rather to use the antimatter as a way to catalyze fission. So to take something like uranium, even just natural uranium 238, and just spritz it with a little bit of antiprotons and get those U-238 atoms to undergo fission, and then direct the fission daughters, the little particles that shoot out at about 3 or 4% the speed of light, to then electromagnetically direct those particles backwards. And that is a kind of a rocket that can get us to probably 10% the speed of light. To get faster than that gets difficult because it's still a rocket, still has to obey the rocket equation. But that could probably do a flyby mission with on the order of kilogram of antimatter. And this particular researcher, Joel Jackson, knows a bit about this because his day job used to be making antimatter at Fermilab. So he worked at the particle accelerator near Chicago and produced antimatter. And he has some ideas about how we might be able to make an antimatter factory. And it wouldn't be the size of the Large Hadron Collider, but it wouldn't fit into your university lab. It would be a facility on the order of gymnasium or something. And it would take a lot of power. Just again, going back to energy, it's going to take just a lot of energy. Just work out the kinetic, the 1/2 mv squared, the kinetic energy you need to put into a spacecraft to get it to these speeds. That energy's got to come from somewhere. So that's, I think, quite promising idea. I would probably put that as plan A or plan B on my list. I think that kind of vies right now with the laser-driven light sail, the breakthrough starshot architecture, is probably being the two most promising contenders for doing an interstellar mission in our century.
I mean, if you went back to just the basic fundamentals, just started from scratch and thought about what would it take to make antimatter? Because I don't really think of antimatter as I think of it as almost like a battery. Like you have to take energy,
exactly,
generate antimatter, contain it, and then use it. You, as you said, you just spritz your uranium, or you collide it with matter to create gamma radiation or whatever. If you were sort of go down to first principles and sort of stack up the technology, where do you think it would lie in that idea of an antimatter factory? How much are we looking at?
In terms of cost? Or?
Yeah.
I mean, it would be on the order of something like the Large Hadron Collider in terms of cost. So it's not as big an accelerator. It does not need to reach as extreme of energies. It would need to be designed and optimized to produce antimatter. So what Joel Jackson always is careful to say is when CERN or Fermilab had made antimatter in the past, they were making it for fundamental physics experiments, where they were counting the antiprotons that they were making. They weren't trying to maximize the production. So the design and the engineering would be different. But just the energy cost to run that machine would be, comparable to the cost it probably takes to run the Large Hadron Collider. So it's a big buy-in, but I wouldn't rule it out, because I think the public would be interested in this. The public seems to support the Large Hadron Collider in order to discover the Higgs boson, which, let's be honest, how many people really can appreciate what the Higgs boson is? It's probably counted in a few hundreds or thousands of people in the world. I'm certainly not. I mean, I'm a big supporter of high energy physics and was very excited by the announcement of it, but it's not my field. I can't really have a deep appreciation for it.
But it does feel like a fundamental technology, though. Like having antimatter production, you could imagine a ton of hopefully peaceful uses. You can imagine weapon uses for it as well. But
that's a concern. There's medical uses probably for it, but it would probably be a single purpose facility to make the antimatter you'd need for the interstellar mission. In fact, maybe you would even want to build it off Earth.
Right.
It might be a good idea just to address those concerns that I can already see, percolating up in your mind and your listeners' mind about what else can be done with antimatter.
They make a pretty nasty bomb.
So, to avoid that, it might be good to do it in space.
Yeah. So I want to talk about this paper that you were a member of fairly recently. Explain the idea, because there's a lot of moving parts here. So,
right. So the idea is this comes back to this idea of energy. Is no matter what you're going to do, build the giant laser to push the light sail or make antimatter, the amount of energy is pretty staggering that we need for interstellar flight. And there's arguments to be made that maybe we're not going to have enough energy till the 23rd century. There's a calculation you can do and just say, how much energy do we have available now that we spend on things like launches of spacecraft and probes? And then what fraction is that? Of the energy we have available as our civilization? And then you can sort of extrapolate that forward, and maybe we won't have enough available disposable energy till the 23rd century. So maybe Star Trek had the timing right.
Yeah.
So if you're not willing to wait, then it's interesting to think about other sources of energy you can use. And in the last couple of decades, there's been some interest in thinking about how we can use the solar wind. How can we use this stream of charged particles coming out from the sun? Now, traditionally, people thought it wasn't worthwhile to use the solar wind, and solar sails do not use the solar wind. So solar sails use the photon pressure that comes out from the sun, and that is tens of thousands of times greater in force in terms of the momentum that photons have in comparison to the solar wind. So in the past, people thought solar wind not worth considering. But the possibility is that you can interact with that solar wind via a magnetic field. So you don't need to build a physical sail. You might be able to build a relatively compact device that can interact with that solar wind using magnetic fields, and maybe a small antenna-like device, only meters in size, could interact with hundreds of kilometers of that solar wind. And by deflecting the particles of the solar wind, you do generate thrust. You do generate a force that's transferred to your spacecraft. So the last, I would say, 20 years, there's been all kinds of interesting ideas about how we might be able to exploit that. But all of them are just drag devices. So you might have heard of the magnetic sail or the e-sail, or the concept that our work is kind of based on is something called the plasma magnet. But all of these are just drag devices, kind of like a parachute. So you throw out this magnetic parachute into the solar wind, and it just drags you out from the sun. Now, there's a lot of cool things we could do with that. I'd be happy to talk about, like it's a fantastic technology to get out to the solar gravitational focus and other destinations.
Yes, please. That would be great.
But what led to this paper was, is there a way to get faster than the wind? So our collaborator on this, Jeff Greason, who's with the Tau Zero Foundation, had been exploring different ways to get faster than the wind. And then I had always been intrigued by this phenomena called dynamic soaring. And this was something that was first observed in birds. In fact, goes back to Leonardo da Vinci in his notebook, sketched out. He noticed birds doing these kind of spiraling maneuvers when there was regions of wind shear. What those birds are doing is kind of bouncing back and forth between two different regions of wind. And with that, they can extract energy from the wind and get faster than either of the two wind streams they're interacting with.
Wow. And
now recently, glider enthusiasts, so particularly remote control glider enthusiasts, have exploited this effect. And there's a gentleman named Spencer Lisenby, who has taken small remote control gliders and just launched them by hand. There's no propulsion, no propellers, nothing, no kind of engine on board. But he finds regions of wind shear, like over a hilltop, and he can fly these gliders in and out of regions of wind shear and get them up to almost 900 kilometers an hour.
What?
In fact, they're actually pushing into the transonic regime. Wow. So if you just go and search on Dynamic Soaring glider, you'll see videos of this, and you almost cannot even see these gliders. They're going so fast. They're just whipping around at almost 1,000 kilometers an hour. And they're going like 10 times faster than the wind. So maybe the wind is only going 80 kilometers an hour, but they're able to extract energy between the blowing wind and the stagnant wind on the leeward side of the mountain to get these little remote control gliders going to these extraordinary speeds.
I mean, that feels like there's some kind of application in passenger flights or cargo flights or something. It's
pretty intense. If you watch the videos of this, sometimes these gliders, the G forces are so enormous, they just get ripped apart in flight. So the G's would probably be more than a passenger would be willing to take. But you look at that and you think, gosh, there's got to be some way we can exploit this using these sort of plasma parachutes that might be able to operate in the solar wind.
And so are there differences in speeds in the solar wind that are similar to winds on Earth?
So that's what our paper, there's a section of it, we sort of explore where in the solar system are these regions of wind shear. So one is, we know from the Ulysses spacecraft that kind of went over the poles of the sun, we know that the wind blowing out from the equator of the sun is at about 400 kilometers a second. And the wind coming out from the poles is at about 700 kilometers a second. Now, these things vary. You know, there's space weather, and they vary, sun cycle and everything else. But that's one example of wind shear. So that's one place that we explored in the paper. You might be able to do some kind of dynamic soaring like this, is between the fast and slow solar wind. And then as you move further out in the solar system, there's a feature called the termination shock, which we know for sure exists now because the Voyager spacecraft flew through it and measured it. And a shock wave is also a region where you have fast and slow wind. So upstream, flowing out from the sun, there's supersonic wind. Then through that termination shock, the wind drops from like 400 kilometers a second down to 100 kilometers a second. So you could fly in and out of that termination shock and extract energy. And then further out, there's the heliopause, where the wind almost comes to rest as it merges in with the interstellar media. And so that provides another region where there's different wind speeds. And so we can kind of dip in and out of those regions. But when you start to go fast, so our goal was to get to, some fraction of light speed. We think we can maybe use this technique up to 2% the speed of light.
Really?
When you're going that fast, the solar system gets to be a pretty small place. So just maintaining the curve to stay on these features like the termination shock or the heliopause gets to be a challenge. That's kind of what limits the technique is you run out of solar system.
Right. I think about that idea. People talk about gravitational assist maneuvers, and you're going to try and do a slingshot, and you can use the sun, you can use Jupiter and all of these places as ways to do slingshots, but eventually you're just going so fast that you can't make it back to get another slingshot.
Exactly. Yeah.
But I mean, the influence of the sun reaches out, as you say, to the termination shock, out to the, quite a ways away from the sun itself. But then I think about the interstellar medium as well. Are there different speeds of interstellar winds that you could then ride from that point forward?
Yeah, perhaps. So this actually goes back quite a ways to something I think you probably know quite a bit about is galactic cosmic rays. So where do galactic cosmic rays come from? And one of the first hypotheses that was put forward by Enrico Fermi back in the 1940s was maybe charged particles just kind of bounce off different regions of the interstellar medium that could be moving at different speeds. And that's called Fermi acceleration. Unfortunately, that model didn't quite predict the right power law distribution of galactic cosmic rays. So Fermi followed up with a second paper where he suggested, well, maybe it's shock waves. Maybe there's shock waves in the interstellar medium, and charged particles kind of bounce off the different flow on either side of the shock wave. And then in the 70s, astrophysicists look much deeper into this, and that looks like my understanding. Again, I'm not an astrophysicist. I just read the papers. It looks like that is kind of the main thinking about where galactic cosmic rays, how they get accelerated to such high speeds, is bouncing back and forth on either side of shock waves. And so that could be a way we could use this technique. You might think about a spacecraft. Again, the matter is so tenuous. You have to be very clever in how you extract momentum from such a tenuous flow, but it might be possible to do that, to find regions in the interstellar media where you have these different regions of wind speed and you could keep bouncing off of them and keep extracting energy.
It's such it's a romantic kind of notion when you imagine you've got this spacecraft that is following this course, accelerating, shifting to different zones of wind speed until it finally breaks out of the solar system, and then it's plying the trade winds of the Milky Way to go from star system to star system, looking for different ways to accelerate, making gravitational assists as it goes, and so on. That if in the future we could have this really accurate map of the Milky Way and all of the wind speeds, you could follow these various pathways. So describe what a mission might look like using this technique and the underlying technologies.
Okay, yeah, maybe we could get into the technology of this a little bit, because it is going to require a couple of steps beyond where we're at now. So and I'm going to give a little credit to the ideas that led to this. So this really starts with in the late 1980s, Robert Zubrin. And this is work Zubrin did before he did the famous Mars Direct and Case for Mars work. Was asked by a Boeing engineer, Dana Andrews, to think about, is there a way we could extract particles from the solar wind to use them as propellant, as reaction mass? So is it a bit like the idea, maybe some of your listeners know, the Bussard ramjet? Is there a way we could scoop up matter and accelerate at the back? And so Robert Zubrin was doing these calculations and found that he just couldn't make it work. He was getting more drag from the scoop than he could get from accelerating that collected mass with, for example, an ion engine. So at some point he said, well, let's just throw away the ion engine and just use this magnetic scoop like a sail, or again, like a parachute. So his idea was to take a big superconducting cable, and this was shortly after the discovery of high temperature superconductors. And we all thought we were going to have in a couple of years room temperature superconductors. Just have a big superconducting loop, and that would create like an artificial magnetosphere. And that would be the drag device. And that idea is still so promising, but it would be nice not to have to deploy a 100 or 1,000-kilometer diameter cable. So the next idea that came along, also from University of Washington, so Robert Zubrin was at University of Washington, Seattle at that time. The next idea that came along was Robert Wingley at UW Seattle, who thought about, could we create an artificial magnetosphere that doesn't have a cable? So his idea was called M2P2, so mini magnetosphere plasma propulsion. And the idea was to maybe inflate a plasma by injecting propellant into it. That idea turned out to have some issues. So it's not, we can't completely rule it out, but I think most people who've done analysis on this concluded that you probably can't inflate that plasma and keep it attached to the spacecraft and transfer the energy to it. But it stimulated a lot of thinking on this. And a few years later, one of his collaborators, also at University of Washington, Seattle, named John Slough, came up with the next idea called the plasma magnet. And this is has much lower uncertainty in it. We're fairly convinced it's going to work, and it's been tested in his plasma wind tunnels, which is you just take a magnetic, you take a coil and just rotate the magnetic field and start the electrons that are in the solar wind circulating around. So you basically start driving a current through the electrons that surround the spacecraft. The electrons, very little mass compared to protons, so it's easy to grab onto them and start circulating them. And that makes a current which builds up its own magnetic field, and again makes a huge artificial magnetosphere. So that idea we think will work, but the next step is someone has to test that. That has to be tested with ideally some kind of CubeSat mission, and maybe we can talk about that in a minute. Now, our idea goes a couple steps further. Our idea then, which we did in collaboration with Jeff Greason, is if you have a drag device, you can now use that to extract power. You have to stroke that through the solar wind blowing past you to generate power. So we have to operate that a bit like a windmill, or a bit like a parachute that you reel out on a winch to extract power, and then collapse it, reel it back in, and then let it reel itself out again to extract power. So we're using that predominantly as a power extraction device. And then the final step we need to take that power and launch waves sideways to the spacecraft. Yeah. We need to take the media around us and launch it sideways so that we get a force perpendicular to the wind. And a force that's perpendicular to the wind, that's what is called lift in aerospace engineering. And if you can generate lift, then you can start to do these dynamic soaring maneuvers like birds do and like these remote control glider pilots do. So we got to pile three technologies on top of each other to pull off this trick.
Right. And sorry, you mentioned power. So are you actually generating electricity at the same time for your spacecraft?
Yes. Yeah. So you need to generate electricity, and then most electricity you use to then launch plasma waves sideways to generate this sideways perpendicular force that is a kind of lift.
Right. You're essentially trying to act unevenly with the plasma wind that's coming from the sun.
Exactly. Right.
Okay. All right. So now I'm sort of imagining some kind of vehicle that is burping out plasma waves, that is reeling out various. Again, this is still just going back to, it feels like a sailing ship. But anyway, it's reeling out various devices to harvest power and change its direction. So what happens next?
Okay, so if you can get all these technologies to play together, then you can generate lift, and so you might launch from the Earth, go out and find this interface between the fast and slow solar wind in the solar system, and maybe bounce back and forth between that a couple of times, and that will kick your speed up to hundreds or even 1,000 kilometers a second, and that is screaming fast. Yeah. So at those speeds, within a year or two, you can get out of the solar system and get out to the termination shock, and then you would kind of arc along the termination shock and dip in and out of the fast and slow regions on either side of that. And within 2 years, you can get up to probably 2% the speed of light. But that's still not fast enough to get us to where we want to go. So at that speed, it's still going to take 100 years more to
Right.
get to Proxima Centauri. So there's some other ideas that our collaborator Jeff Greason has.
But what about on the other side? Like, can you run this machine in reverse to slow yourself down and go into orbit?
Yes, yeah. Actually, these kind of magnetic parachutes work very, very well as decelerators. So if you're coming into a solar system, and there's well, first of all, you probably start the braking a couple years out. So you can do a similar trick. You can do this plasma magnet technique where you start inducing a current in the electrons that are in the natural interstellar media around your spacecraft, and make a magnetic structure that starts to brake against the flow of charged particles going over it. And then as you enter the target solar system, if there's a solar wind there, we're not sure there's a solar wind coming out of, Alpha Centauri AB. Probably should be, because they're pretty similar to our sun. But if there's matter streaming out, then we can brake against that. So it is a promising way to do a deceleration, which, as you know, for interstellar missions, that's, one of the challenges is, even if you can get there, how do you slow down to actually go in orbit around the star?
And when you think about it, you've got the two stars that are relatively close together. There's got to be all kinds of shenanigans that their stellar winds are getting up to. Lots of opportunity to exploit the various shear forces.
Yeah.
Yeah, really interesting. Okay, so and then before I interrupted you, you were going to then figure out a way to happen within our lifetime, as opposed to something that's still going to take generations for it to accomplish.
Right. So the next technology piling one more on here is our colleague in this work, Jeff Greason, has proposed that if you can get up to 2% or faster the speed of light, you can start to then again interact with the wind blowing over you. So at that speed, you punch out into the interstellar medium, which is more or less at rest. It's kind of in the rest frame of the galaxy. But since your spacecraft is moving, it's at 2% the speed of light or so, you could maybe extract energy from the wind blowing over your spacecraft and use that to launch reaction mass out the back. And this is an idea that Jeff has developed, called the short name for it is the Q drive. So in aerospace, we refer to the dynamic pressure, the pressure that you get as you fly in to air that is at rest, but from the cockpit looks like you see air flowing towards you. That dynamic pressure is called Q. So he has proposed that, again, using these techniques of stroking a magnetic structure through that wind, you can extract power, and you can use that power to launch reaction mass out the back. And essentially, you're concentrating the kinetic energy that's already in the spacecraft into a smaller mass that is the residual mass of the spacecraft after you've expelled mass out the back. So this is called the Q drive, and this one really stretches your brain. Okay, so I remember when Jeff first presented this at one of the Interstellar Symposium a couple years ago, I just got up, walked out, went back to my hotel room, and just rocked back and forth catatonically for about a day to process this. And then came back the next day, found him, and said, "No, I think you're right."
Right.
So this is like
Yeah. Like, I understand this idea, like momentum, like the 1/2 mv squared. That
exactly. Yeah.
That if you can decrease your mass, you can increase your velocity, and you are cannibalizing the mass of your own spacecraft to generate velocity. You're back to the rocket equation.
Right, but it's actually a little bit, when you get faster, it's a little bit better than the rocket equation, because your rocket equation, you're carrying all of your propellant and all of your energy on board. And this idea is you carry some propellant on board, but you're getting your energy from the surrounding media that you're flying through. So it's a bit, I'll give you maybe an aerospace analog. If your listeners are aware of a technology called the ram air turbine. So if an airliner is flying through the air, and it loses power, so there's an emergency, the engines go out, most airliners have a little windmill that drops down called the RAT, the ram air turbine. So it's a little windmill that generates power just to keep the aircraft powered for emergency. You still need power for the instruments and so on. So imagine you were on an airliner and this happened. You lost all your engines, and the little ram air turbine dropped down, started generating power. And you said to yourself, wait a minute, I have power and I have mass on board. I have water that we use for the restrooms and making coffee and everything else. What if I use that power to shoot water out the back to generate forward thrust. So you wouldn't do that in an airliner because you're only going 1,000 kilometers an hour, and there's not that much kinetic energy stored inside that water. But if you were going already at 2% the speed of light or 5% the speed of light, at 5% the speed of light, just the kinetic energy of anything, you, me, water, waste, is actually greater than the energy that's contained in fusion fuel.
Wow.
So this is Jeff's idea, is you extract power and you use that power to launch reaction mass out the back and concentrate the kinetic energy that's in that reaction mass into the residual mass of the spacecraft. So all this has to be done with a lot of efficiency. So that's, I think, probably the biggest unknown is you would need to be able to extract power. The windmill needs to operate at relatively high efficiencies. And we probably just don't know enough yet to see if this is, so it's probably not number one on my list right now of most promising interstellar technologies. But there's a lot of work to be done here. It's kind of cracked the interstellar problem wide open and thinking about finding ways to exploit sources of energy that already exist in space. And we just kind of cracked the door on this. I think there's a lot of interesting ideas. I think a lot of your listeners who know a lot about astrophysics and other sources of energy in space, hopefully this catalyzes further thought. There's a lot of energy in our solar system. There's a lot of energy in the universe. And you just have to think about how to tap into it. And so what we found in our work is you kind of need to find two media at different speeds. Okay, so if you can find a fast and slow solar wind, or if you can find particles at rest and particles moving, and you can interact with both of them at the same time, then you can extract energy.
And I mean, obviously this, you've done the math and you trust that this doesn't seem to violate the laws of physics. It's just
right. We're conserving energy, conserving momentum. That's all fine.
Right.
It's just, is there a technology now?
Right.
Is there a way it can be done?
It's an engineering challenge now.
Exactly.
Yeah. And so, but based on sort of back of the napkin calculations, what do you think would happen with the velocity profile across the mission? Then you've exited the solar system at 2% the speed of light. You've deployed the propeller.
The propeller, the windmill. Yeah. So you'd probably spend another couple of years accelerating up to 10% or 15, 20% the speed of light.
Wow.
And then you would probably coast for a decade. And then as you approach your target solar system, you'd deploy again one of these drag devices and start decelerating. And then as you enter the solar system, if there's a solar wind there, you can decelerate harder against that.
Right. And decelerating is easier than accelerating because, sort of in the same way, like the Orion capsule, like it was launched on the top of a gigantic rocket to get out around the moon. And then when it came back, it decelerated through the atmosphere down to a soft landing in the ocean because it was taking advantage of all of the atmospheric density to slow itself down.
Right. So the challenge is, interstellar media is very, very tenuous. There's, in a given cubic centimeter, there's maybe one proton there if you're lucky, probably less. It's way better vacuum than we create here on Earth. Even low Earth orbit is better vacuum than we can create in a laboratory here on Earth. So it's this incredibly, incredibly tenuous media. So that's why we have to think about how to generate enormous structures that have no mass. Okay, very challenging, but that's what a magnetosphere is. That's what Jupiter's enormous magnetosphere is. It's using the rotating magnetic field of Jupiter to grab onto the charged particles. In Jupiter's case, it's the electrons and the ions, and rotate those and create this enormous magnetic structure.
I get questions and comments all the time from people who are watching some of the videos, and they're sort of having those out of the box ideas. And I'm sure people listening to this right now, they're like, all right, well, like what have we got, right? We've got cosmic rays, we've got photons coming from other stars, and we've got other charged particles that are being generated, the cosmic microwave background radiation itself. Which things could you throw into the mix that would have a noticeable effect, and which things are just so low that they just can't have an impact on what you're doing?
Yeah, I mean, I think they're all worth thinking about, but just an easy calculation to do is just think about what the energy flux is. So things like, cosmic microwave background, and those are pretty low energy photons. So I wouldn't rule it out. I mean, I think it's fantastic if people want to think down these paths. I think there's a lot of possibilities out there, but the simplest calculation to begin with is just think about what energy is available. Okay, so just look for sources of energy and think about the density of the sources of energy, and then from there we can start thinking about the technology we might use. So right now, the most promising thing we've been thinking about is the solar wind, and again, trying to find where there's regions of two different velocities, so you can exploit this technique.
So, I mean, it's interesting to me whenever I hear these kinds of ideas. Same thing with the laser sailing. The goal is to figure out a way to travel to another star system. And that's a fantastic goal. But the reality is that our own solar system is poorly explored. There are tens of thousands of locations that if you would ask a planetary scientist, like, would you like some close-up pictures of this Kuiper Belt object? They would say, yes, please. How can we sort of adapt this technology to make missions that would happen here in the solar system?
Yeah, we could. To be honest, I am getting a little bored with our solar system, so I'm going to give you a little pushback here.
All right.
I'm not a planetary scientist. I'm sure if I were a geologist, I mean, people often ask me, and if she gets asked this as well, is do you want to go to Mars? And I'm actually not that interested in going there personally. But I'm sure if I were a geologist, a planetary scientist, I would love to spend the rest of my life exploring Mars. I'm sure for that community, it's very, very exciting. But I want to get back to the excitement that we saw with Voyager and New Horizons. So I was old enough to remember Voyager. Jupiter said I was pretty young in those days, but I remember the Uranus and Neptune flybys quite well. I was a teenager at the time when those happened. Too. And I remember seeing the videos, watching the documentaries about it, and when those first pictures would come in of volcanoes on Io and ice cracks on Europa, and you would just see the scientists, just their jaws drop, just the sheer thrill of that. And in my mind, I kept saying, like, I'm missing out on this. This is it. I remember when Voyager flew past Neptune, they said, that's it. The initial reconnaissance of the solar system is done. We got one more thrill with New Horizons at Pluto. But I'm getting a little bored. I mean, I'll challenge Fraser here. If I opened up a picture of the asteroid Bennu, and I opened up a picture of the asteroid Ryugu, the one that Hayabusa 2 flew by, you almost can't tell the difference between them, right? So I'm sure there's a lot of excellent
science. And add Dimorphos now to the list.
Yeah, they all look more or less the same. So I'm sure there's a lot of wonderful science that's going to be done by that community. But I want to get back to kind of those jaw-dropping, thrilling moments that we got. And I think the only way to get that feeling back is to go interstellar, is to think about getting an image, a multi-pixel image of an exoplanet. I think the solar gravitational lens is probably the nearest term technology that let us do that. But getting to your question now, how can we use these technologies in the solar system? We can. So this, for example, the plasma magnet, these sort of drag devices that drag you out in the solar wind, you can get to Mars in a week if you want using that technology. It's hard to slow down when you get to Mars. Again, how do you brake when you get there is a challenge.
Right.
But I'm not sure we really need that. I don't know if the science community wants to get to Mars that fast. But
they do want to get to Neptune in a month.
Yeah. But I think I'm going to let out a little dirty secret here is I suspect, and I have some personal experience at this, that the science community actually likes these kind of decadal missions. If nothing else, it's good job insurance. And they use that time very, very well. So when New Horizons was launched to Pluto, they didn't just, go to sleep for 9.5 years. That team worked very intensively through that entire 9.5 years to plan the flyby, prepare for it, do rehearsals and so on. And I had a little experience with this. I had an experiment that flew on a European Space Agency sounding rocket. It was not an orbital experiment. It was a microgravity experiment that we flew. in 2017. And when that was initially funded, it was going to fly in 2013. And as happens, as you probably know, with space missions, there's delays and things get pushed back no earlier than. And every time we got pushed back, we'd say, oh, darn, we're not going to get that mission off. But secretly, it was a little bit of job insurance. It was guaranteed that our funding would keep coming, that we could use this program to support master's, PhD students. So I may not have wanted to let that cat out of the bag. Right. I may never get another mission again after admitting to this. But I think it's something similar with the planetary science community. When you read the decadal surveys that they produce, they're really focused on thinking about the science they can do with the technology that we have, basically chemical propulsion. And they can, they're very interested in going back to Uranus and Neptune, exploring Triton. And I think these are fantastic missions, but they can all be done with current chemical propulsion. And I think what we really need to do is find missions that can't be done any other way, that really require these kind of advanced propulsion concepts to get the science community on board. And then when you get the science community on board, then the funding comes. So once you start saying, here's a mission that can only be done using some advanced propulsion technology that's at TRL2 or TRL3, things that are sort of NASA NIAC level. Once you get the science community to recognize they need those technologies, then the funding will come, and then I think these things will happen. So that's why I'm very keen on, I think, solar gravitational focus. I think that is sort of the killer app for these kind of drag devices that just get dragged out in the solar wind, and technologically much simpler than the tricks we're proposing to play, where you extract power and generate lift and so on. Just a pure drag device like this can get you to the solar gravitational focus in less than 10 years, wow. Which I think brings it into the realm of the feasible. Yeah. Whereas the current thinking of using maybe a solar sail to get to the solar gravitational focus will probably require 20 years. And that's long for even the very patient planetary science community and astronomy community to wait.
Right, yeah. Now, one of the other things you've done is built one of the fastest guns in the world.
Okay, yeah, I'm glad you brought that up. That was one of my previous projects.
Right.
So, yeah, my background is I'm an aerospace engineer by background, but I've always kind of been drawn to these extraordinary concepts where you're kind of pushing up against the limit of things. So at McGill University, I, for the last couple decades, have run a lab where we study explosions and detonations, but my interest there was always, again, thinking about advanced propulsion and how can we use this to launch things that get faster than anything else. So over the last 15 years, with support from the Canadian Space Agency, we developed a kind of hypervelocity launcher, kind of a gun, not a military gun. You wouldn't want to use it personally for reasons I'll get into in a minute, but it's a laboratory device that can launch little pellets up to faster than 10 kilometers a second. And the purpose is to look at the impact of orbital debris, to look at micrometeorites, but really mainly orbital debris. So the way this gun worked was actually using high explosives. So we would take a kind of a gas gun and then wrap explosives around it and detonate those and squeeze, kind of like how you squeeze a tube of toothpaste. You'd squeeze gas to very high pressure and temperature, and then use that to launch a little pellet up to these speeds, actually greater than we got over orbital velocity. We even now got over 12 kilometers a second, so we can even get faster than escape velocity.
Right. I think of like escape velocity is like what, 12.1 kilometers
I think it's
per second.
11 something. Yeah.
Okay,
so we're just over escape velocity. Of course, we can't shoot anything into space because our little pellets would be vaporized in the atmosphere. So we have to do all this in vacuum.
But in theory, you could fire, if there was no atmosphere, you could launch projectiles off Earth into the solar system, which is...
That's right, yeah.
But, and like, that's got to be humbling when you see, like, there are particles moving around in the solar system, little pieces of dust and debris and stuff that are moving at those kinds of speeds. What does that do to a target that is unfortunate enough to be hit by it?
Yeah, nothing good. Okay, so yeah, at those speeds, the energies are just incredible, right? So a good number, I use this number a lot in my research, is at about 3 kilometers a second, any object's kinetic energy. So you, me, my water bottle, if it's moving at 3 kilometers a second, its kinetic energy is equivalent to the explosive energy of a mass of TNT that has the same mass as that object. Okay, so my 1 kilogram water bottle here, if it was going at 3 kilometers a second and it hit a wall, the amount of energy it would release would be equivalent of about a kilogram of TNT. Okay, but things orbiting around the solar system, like the Earth, is orbiting at 30 kilometers a second. So right now, you, me, my water bottle is moving at 10 times that speed. And because kinetic energy is 1/2 mv squared, this water bottle is actually equivalent of 100 kilograms of TNT. So right now, this is like 100 kilograms of TNT. We don't notice that unless it were to hit something at rest. So that's what would happen if an asteroid hits us. Or worst case scenario, if a comet hits us that's coming in, comets can be coming in at 70 kilometers a second. So now that's the equivalent of hundreds of times the mass of that comet hitting us in explosives, and that's pushing up to extinction level
right.
events. So it's a lot of energy. But going back to our earlier conversation, gosh, is there a way we could use that energy? So that's some of the work I'm working on now. Is we're toying with some ideas here at McGill about thinking about how could we possibly extract energy from asteroids or comets, because there's a lot of energy in their motion.
But I think about like just the amount of damage that these kinds of things can do to spacecraft. And if you then take this and scale up to 2% the speed of light, suddenly you've got grains of sand that are like tons of TNT.
Right. So that's actually the probably the biggest concern I have about the breakthrough starship architecture. So I think there's very little technological uncertainty. I mean, we know photons have momentum. We know the laser sail will work. We have a technology to scale up the laser now. A concern I have is, when that sail is being accelerated by the laser, if it hits dust grains, which it will, even during the relatively short, like 3-minute acceleration they're planning on using for the breakthrough starship, it will hit dust grains. One of those little dust grains, when you're going at 10% the speed of light, is not like an atomic bomb going off, but it's several joules of energy. It's about like a starter pistol going off. And that, if it damages the sail, and that sail is no longer perfectly reflective, if it starts to absorb some of that laser energy, it could just vaporize the entire sail. So that's some other work we're doing at McGill. We're looking at how can we maybe clear away some of the dust grains in front of the sail. So one possibility is you may want to make the sail a little bit partially transparent, so that the laser light that goes through could maybe vaporize, clear away some of the dust grains, kind of like a cow catcher on an old steam locomotive, that it would kind of push the dust grains aside or vaporize them before they hit the sail. Once the sail is up to speed, you probably turn the sail and fly it edge on. So that's the current thinking. The light sail would probably turn and fly edge on, and you could probably shield that little exposed leading edge. But a real concern is when it hits the dust grains, when the laser's on and it damages the sail. That is a reason why we shouldn't put all of our eggs in the laser light sail. There may be some showstoppers that might show up.
Now, you mentioned, though, that you're trying to think of ways that you can extract energy from asteroids, comets, things like that. What's your thinking on that?
Okay, so this is something I've presented. I haven't written a paper on it yet, but I've presented this at a couple of conferences. So it might be possible to sort of bounce pellets back and forth between different asteroids and comets. There's a researcher at Cornell named Mason Peck who had some interesting ideas. He and his PhD student, Zach Manchester, started this idea of little tiny chipsats, little sprites, little tiny spacecraft. And again, if the spacecraft gets very, very small, it could have a significant amount of electrical charge compared to its mass. So it could start to interact electromagnetically with magnetospheres and so on. And Mason Peck developed this very romantic idea I like of converting our solar system into a particle accelerator. Is there a way we could use Jupiter to accelerate these little chipsets up? So we've been playing with that idea, and it's again hard to find. You were talking about earlier, you do a flyby Jupiter, you can do that at 10 kilometers a second. But if you're going at 10% the speed of light, forget it. You just zip by. And
you get one.
You don't get much gain, right?
Yeah.
So you would probably need to build some kind of artificial magnetic track to keep bouncing your particles back and forth. And if you have to build it artificially, then you could attach that to anything. So there's some interesting asteroids in our solar system that are actually orbiting retrograde. They're orbiting the wrong way. And you could imagine maybe having a track on one asteroid and a track on the other and just bounce pellets back and forth. Kind of like if you had two trains approaching each other and you were to throw a tennis ball and let the tennis ball bounce back and forth, each time it bounces off one of those approaching locomotives, it picks up twice the speed of the locomotive. And perhaps we could play some kind of trick like that. But again, it's wide open, and I think for your listeners, if they want to explore this, just look for any place in our solar system, in our galaxy, where there's sources of energy, and even if it's kinetic energy, like you, me, my water bottle have, if you can find another mass that's in a different reference frame, it's moving at a different speed, then technologically there may be ways to tap into those different those masses moving at different speeds and extract energy out. So I think it's a whole new area.
One of the, a lot of these techniques that you're discussing work because you're in space and the forces are roughly balanced on you for you to be able to move from one, like an ion engine, for example, can't get you off Earth. But once you're in space, then you can accelerate for days, months, weeks, years to reach velocities that a chemical rocket could never reach. And so far, the best idea that we have for getting payloads off of planet Earth is chemical rockets. What do you think is the best way to get payloads off of planet Earth?
Yeah, right now it's the chemical rocket. So I worked really early in my career when I was a graduate student. I worked a bit on the gun launch to space idea, the Jules Verne de la Terre à la Lune. I worked on a technology called RAM accelerator in the 1990s. It looked really promising as a way we might be able to shoot things off the Earth. And then, ironically, my lab at McGill, where I do my research, dates its legacy back to Gerald Bull. So if people know this story, there was a McGill professor in the 1960s who got very close to launching a satellite into space using gun launch technology. So I thought that might be a neat way if we could never get rockets to be reusable, then just to launch bulk mass into orbit. Impulsive launch, gun launch might be a way. There's this company you probably know about called Spin Launch that's looking at this now. They can use like a sling to get maybe the first 2 kilometers a second to get towards orbit. But the reusability challenge has been solved now. I mean, just incredible what's happened in the last 5 years with SpaceX and everyone else who's following along in their path. So I think that problem has more or less been solved. And
so you think like a 2-stage fully reusable rocket is, at the end of the day, the most reasonable way to get payloads into orbit?
Yeah, I think so. I mean, I have colleagues that are working on other ideas, and total props to them. Keep trying.
Yeah.
But right now, I think the revolution that's happening is it's going to happen. Even if SpaceX should trip and fall with the Starship, as ambitious as it is, there's other companies that aren't quite as fast, but are coming along behind, Blue Origin and Relativity and Firefly. And there's a lot of other companies out there waiting in the wings. If SpaceX should trip and fall, that will pick up the torch and bring it forward.
Yeah. And there's probably a handful in China as well.
Yeah, when I advise students, I say maybe don't try to get into this race. Let's sit back and assume by the time you graduate, this is going to be solved problem, and think about where do we go next? What's the next kind of disruptor that we need to really open up the solar system and then eventually go interstellar.
Yeah, people bring up these ideas like, what about a space elevator? What about a launch loop? What about an orbital tether? And so on and so forth. And there are all these mega projects. And it's really hard to compete against a giant stainless steel rocket being built in a field somewhere that, if it does become fully reusable, out-cost competes those enormous mega projects on a price per kilogram.
Right. I mean, I'm a big fan of all those. I have colleagues that work on the space elevator, and total respect and props to them. But even if you want to build a space elevator, the best way to get it done is to hope that these companies are massively successful and we build an enormous infrastructure in space where we're delivering megatons of to orbit every year.
Yeah.
And then eventually there'll be a demand for something cheaper. And also, I think eventually environmental concerns will come in. I mean, eventually, if we're really launching this many rockets, there'll start to be questions raised about what dumping all this exhaust into the stratosphere is doing. And eventually there'll probably be an environmental reason why we would want to go to some kind of space elevator or launch loop or these other ideas. So
yeah, I sort of think about the future of space exploration, that this time when we're going to want to launch a bunch of stuff off planet Earth is actually pretty short in the long future history of humanity. That we will, once we've launched the basic infrastructure, the fabrication facilities, the various dense technology, we will extract our resources from space. We'll build things in space. There won't be a big need to get payloads off planet Earth, which is trapped down in this gravity well. And it'll just be every now and then someone's going to want to hop on a rocket and go to space. Like that'll be like the last payload. Will just be humans wanting to go to and from space. And there won't be a need to launch large payloads off planet Earth anymore. And the rocket industry will end effectively, I think.
Yeah, that would be a nice day, right? When you do come back to Earth, tread lightly, and I think that has a nice sound to it. That we try to move all the industrialization off the planet and do that out in the vacuum of space, and then we won't need so many rockets. That's a nice vision.
Now you've got a conference that's coming up where people can talk about some of these ideas and present some of their out-of-the-box thinking. Let's talk about that.
Yeah, so thanks for giving me a chance to plug this for a minute. So these ideas that I've been talking about for the last 45 minutes or so evolved out of a series of conferences that are called the Interstellar Symposium. So these are organized by the Interstellar Research Group, which is a nonprofit in the U.S. These conferences used to be called the Tennessee Valley Interstellar Workshop. And they really evolved out of researchers at NASA, in particular Les Johnson, who I know you've had on your program, and people at the Oak Ridge National Lab in Tennessee. So the conference used to bounce kind of back and forth between Huntsville, where NASA Marshall is, and Oak Ridge. It's called the Tennessee Valley Interstellar Workshop. But recently it's been moving around in the U.S., and I'm really excited. Next summer at McGill, we're going to host the first international Interstellar Symposium. So all of the researchers that work on these different ideas, including even the more far out concepts like warp drives and wormholes, they'll all be here. And it's a very exciting time. I think 10 years ago, if I had announced I was going to refocus my research group at McGill University on interstellar flight, my colleagues might have looked at me as being a little disturbed, but in the last 10 years, I think things have really changed. We've had some really significant academics, very respected researchers start to get involved in this interstellar travel field. And so it's starting to become respectable, it's starting to become mainstream. And my real goal now for the rest of my career, I kind of don't want to get into this trap of inventing the next Rube Goldberg way to get to the stars. My vision is to try to build a community where I have lots of colleagues working on this, and we have lots of students working on it, and we have students that can travel back and forth. And that's what it takes. You need to build a village, and once we get a number of researchers working on this around the world, and we have a community where young people, I'm really interested in working on this plasma physics aspect of it, they can go work with another researcher there. Once we hit that stage, I have no doubt we're gonna go interstellar. I mean, I live to see it, but once you have a healthy community like this, it's gonna happen. So we're hoping that the conference we're gonna have, it's gonna be this July 10 to 13 in Montreal. So if you want to look into more of the details on this, just go online and look up Interstellar Symposium. And we've already started to announce the speakers, and hoping to have a lot of participation from people like Fraser and his colleagues, to meet all the community working on these problems.
So place your bets. What year does the first interstellar probe make a flyby of another star system?
I'm going to say it's going to be in this century. I'm going to put myself out there. I think when we start getting closer and closer to the anniversary, when the big 100-year anniversaries start coming around, Sputnik and Gagarin's flight, and then Apollo 11, I think the pressure is going to build from the public. And I'm also predicting that there's going to start to be some pressure from the exoplanet community. Mm-hmm. So right now, I mean, they're in this incredible, you know this community very, very well. I mean, right now they're in their golden age, right? The discoveries that they're making every day, it's some new exciting exoplanet going to be discovered. But I have a feeling that this golden era will start to come to an end when they reach a limit to what they can learn from a single pixel. So right now, when you hear exoplanet astronomers talk about direct imaging, they're talking about taking a pixel. Now they can learn an awful lot from that pixel. They can do spectroscopy and detect trace gases in the atmosphere and so on. But I think we sort of had a preview of this with the phosphine and Venus story, which has been I'm again just a spectator on this, but it's been very, very interesting. So if you think about Venus as an exoplanet, it's bright, right? Like Venus, when it's at its brightest, it's so bright it like hurts to look at it.
Yeah,
right?
Casts a shadow.
All the photons we want from Venus, but we're not going to get this issue resolved as to whether there's life in the atmosphere of Venus until we go there and do in situ measurements, which is going to happen now. There's several missions being talked about that will go and resolve this debate. And I think probably in 2 or 3 decades, again, the exoplanet people are going to have this incredible run of discoveries. And they're going to start discovering trace gases in atmospheres that point towards life, but it won't be unambiguously resolved until we go there and make a measurement. Yeah. And so I think that's when the science community will start to come around and put pressure to develop these technologies that will eventually let us get there. And I think we'll see that kind of mid-century, and then maybe 2061 Gagarin's flight or 2069 Apollo 11. Probably would be a good launch date, I think. I don't know if we'll get images. So what's the arrival
date? I need your arrival date.
Yeah, if we launch in the 2060s and we go 20 or 30% the speed of light, then we get to Proxima Centauri, and hopefully there's planets in Alpha Centauri A and B. If we can find planets there, then we'll get there in 20 years, 25 years, and then got to wait 4 years for the data to come back. So I think it will be by the end of the century. I think it'll be
like the year
21st century.
2100. On the nose?
Yeah, will be the interstellar age, just like the 20th century was the space age.
Amazing. Yeah. I mean, you mentioned this early on, this idea of the weight. It's the weight calculation, that you take the energy use of planet Earth and you just continue its exponential rise, and at the same time you just measure the amount of energy required to send a spacecraft to another star system. And at a certain point, it becomes trivial to do that. And so it's, I think it's in the weight calculation paper, they estimate it's in the 600, 700 years from now.
Yes, I know that paper very well, and I've heard you mention it several times on your program. So I'm glad you brought this up, because I do like that paper very much. It's by Kennedy, written about 15 years ago, called The Weight Calculation. And I give that to all of my students. That's like their first reading assignment when they start working in my interstellar propulsion group.
Yeah.
It's a great paper. I recommend everybody read it. But there's a lot of assumptions that went into that paper, and it's been recently revisited by a German exoplanet astronomer named René Heller, who's going to come here to Montreal for the symposium. I just arranged for him to come. I'm closing the deal with him now to make sure he's here for the Interstellar Symposium. So he revisited that in a paper a couple of years ago. And it's one of these things, it's a bit like the Drake equation, right? So it's a fantastic intellectual exercise. It really helps organize your thinking. But you can get almost any answer you want with how any reasonable person can get any answer they want. So The original paper, Kennedy's paper, assumed that I think we only increase the speed of spacecraft like 1% or 2% a year. And that his calculation is you better wait a couple hundred years. Otherwise, you're going to be overtaken by the fastest spacecraft launched after you leave. And then René Heller revisited this and found that, well, if there's a breakthrough in propulsion, if we bring some new technology on board, like the laser light sail or antimatter or these other technologies, then the numbers all change, and the optimal time to launch might be 2050. So I can send you the new version of the weight calculation.
Oh, that sounds great. Yeah, I'd love to check that out. Yeah.
So it's a great way to have the discussion. But if you can tap into new technologies, or what we've been playing with, this idea of tapping into sources of energy in space, it really changes the calculation. You don't have to buy that energy. You can extract it from some energy source in space. It's a totally different calculation.
What do you think are the fundamental limits to this? Like if you've got some civilization that has existed for millions of years in peace and harmony and is investing a tremendous amount into trying to make the technology better and better and better, where do you think this tops out at?
Yeah, we should be so lucky is probably the first thought I have. I just spend all of my day racking my brain to think about how we might be able to get there.
But now you've got you've got a civilization that has the resources of millions of stars.
Right. I mean, the fact that we have now 3-4 different paths, different technologies that we think should be able to get us interstellar. I mean, get us to another solar system in the next century, then it really does sort of rub your face in the Fermi paradox, right? Because
of course.
If we can do this, we're just not far from the monkeys that climb down from the trees. If we're able to figure this out, then an advanced civilization for sure has been able to figure out how to exploit, black holes and other energy sources to do. And I think you're aware there's concepts out there to do exactly this, to exploit these kind of astrophysical energy sources to do very rapid missions. Even intergalactic travel might be possible. So,
are they moving at the speed of light? Are they expanding their empires at the speed of light, or just shy of the speed of light? Are they? Yeah,
I actually find it a little scary to think about. I actually find, it's a little frightening to think about. I actually find the Hubble Deep Field image for me induces a little bit of terror when I look at that. When you look at all those galaxies and you think that, okay, there has to be life out there, and that life is going to figure out, if we have 3 or 4 ideas we think might work for interstellar travel, for sure they figured it out and have no doubt reached the Kardashev level 3 civilization where they've conquered their entire galaxy, and presumably there's some malevolent form of life out there. If NASA defines, their astrobiology office defines life as something which undergoes Darwinian evolution, and Darwinian evolution is not always very kind to its competitors. It's a little scary to think about what might be happening.
Yeah, there was a paper that I read about this, that like about 6% of the observable universe is reachable if you could go the speed of light, or just shy of the speed of light. That 94% of the universe has already fallen over the cosmic horizon. We could never reach it. But that 6% is decreasing day by day. And the way you get the biggest land grab is you build spacecraft capable of going nearly the speed of light immediately, and you send them to every distant galaxy that you can still reach, and begin that process of your von Neumann probe that begin. So in fact, we should see the expansion. It makes the most sense to expand as quickly as possible, because otherwise you will have less land out there to reach. And it goes back to that same idea, like, why don't we see these gigantic civilizations gobbling up enormous portions of the universe in the sky all around us at nearly the speed of light? And like my preference is to just say, it's too scary to think about.
Right.
I'd rather just assume we're alone. That's why, because they're not out there.
Yeah.
Right?
I mean, if they're coming, they're so advanced, there's nothing we can do about it. I don't think we can hide. If there really is something malevolent out there, then our number's up. So put that out of your mind, and then
don't worry about it.
Yeah, my next answer is then let's just go find out. Let's find out what's out there.
Absolutely.
Let's go see.
Well, Andrew, it's been a pleasure to talk to you. If people want to find out more about your work, what's the best place to do that?
Yeah, so my group has a website. It's pretty simple. It's interstellar flight.space. So if you just go to interstellarflight.space, you can find my research group. And then if you want to find more about the Interstellar Symposium, I think just look up the Interstellar Symposium, Montreal 2023, and you'll find out all the details and the speakers we're going to have at the symposium.
People want to choose this as a career, as an aerospace engineer. Where would, what's the best path for them to go educational wise?
Yeah, I have to say most of my aerospace engineering background had to be thrown out the window. Okay, so most of what I learned about rocket propulsion and ion drives and all this stuff really isn't going to cut it for interstellar travel. So probably the best background is actually in physics. And I do work with a lot of students in physics. Unfortunately, they're always under so much pressure to learn, string theory and the really advanced stuff. They don't always have time to dwell on what we really need is electricity, magnetism, optics. It's really your undergraduate first year physics course. So I've actually been working a lot with, we have this system here in Quebec, the CJEP system. So students between high school and university go to this 2 or 3 year program, and that's where they do their basic physics. And that's a lot of the students I've been working with on the interstellar travel problem, because they're kind of learning E&M and optics and these things for the first time. And so I'm trying to prime them for what to look for. These are the problems that we have. And so as you go through this material and you're learning it for the first time, you don't have any preconceived notions. You might be the one that figures out how best to extract energy from different moving particles. So I think that's the best thing to do is engineering and physics, but maybe try to read about these problems and sensitize yourself what to look for.
Yeah, that's really interesting.
It doesn't need to be, you don't need to understand string theory. You don't need to understand full tensor calculus of general relativity. If you just look for energy, just think about energy, 1/2 mv squared and momentum, mass times velocity. If you just understand those concepts, you can actually contribute to the interstellar flight research. You don't need to be at that high level.
And there aren't a lot of job openings for interstellar engine designer yet. So you're going to have to like do your day job as a fusion designer or working, in photovoltaics while you think about your future space drive.
Right. So what I found has worked well, and this is the pitch I make, is I've actually been doing some corporate fundraising for our upcoming symposium. So the pitch I make to the local Montreal aerospace companies is, if students engage this kind of research early, they're going to have a really fundamental understanding of how engineering and physics is done. They're going to know how to think out of the box. They're going to know how to work on sort of out of context problems. If you give them a problem that no one's ever thought about before, how do you even start to approach a problem like that? So I think the students that have worked on this with me have been, it's been good training for them for research. And actually some of them have moved on to work on fusion energy. So I have a collaboration with a British Columbia based fusion energy startup that you're probably aware of. And some of the students that worked on my interstellar research have kind of pivoted over to that as they mature and go on to graduate study. But again, that's kind of why I want to build a community. If I can get another 6 researchers at universities around the world that are working on this, and we can start to traffic students back and forth with each other, then that's it. Then we have a community, and I think it'll happen. I sort of think about the astrobiology community. So when I was a student 30 years ago, and NASA announced they're going to create an office of astrobiology, there was a lot of snickering and people were pretty snarky about how can you have a field of study where you have n equals 1 data points. That was the joke about astrobiology. But now the astrobiology community does fantastic research.
Yeah.
Open up Science and Nature, and you can see all kinds of fascinating studies they do about the possible spaces of life. Does it have to be DNA based? Are there other possible bases of life? They found a way to carve out really interesting scientific problems around the question of life in the universe, even though we haven't found other life in the universe. And I think that's the challenge for the interstellar propulsion, interstellar travel community, is we have to carve out really good problems to challenge students, to let them write good theses, publish good papers. And if you hit a critical mass of people working on that, it sort of becomes just a self-reinforcing research endeavor, like astrobiology has come. And SETI as well. SETI is now pretty respectable. It's not the joke that it was 30, 40 years ago when Jill Tarter started out. Now it's a respected part of
NASA
astronomy.
organizes conferences for people to search for technosignatures, so they're taking it
Exactly.
very seriously.
Yeah.
Well, Andrew, it was a pleasure talking to you. When you do send a spacecraft to another star system, please let me know.
Okay.
All right.
We'll invite you to the press conference.
That sounds great. Yeah, exactly. All right. We'll take care. You can also get even more space news in my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross who support us at the Master of the Universe level. All your support means the universe to us.